Every diagram you were ever shown told you the same calm story. The Earth goes around the Sunday, a tidy circle, a steady center, a planet on a quiet track. But here is what those diagrams left out. The Sun is not standing still, and it never was. It is being pulled into a slow, looping dance by Jupiter and Saturn, while your orbit itself stretches and turns across the ages. The whole solar system is sweeping around the galaxy at 230 kilometers per second, drawing not a circle, but an unclosing flower it has never once retraced. And the galaxy is falling, with everything in it, towards something so vast and so hidden that we can feel its pull and still cannot clearly see it. The honest answer to how you move through space is not a circle, and it is not the vortex you saw online. It is stranger and quieter and more beautiful than either. Get comfortable, hit subscribe if you're new here, because by the end of this, the word still will never feel quite so simple again. Now, let's slowly ease into this. Part 1. The animation almost everyone has seen. There is a video you have almost certainly watched. It has been shared millions of times, passed between friends, embedded in articles, replayed on 100 different screens, and it shows the planets of the solar system moving through space in a long, elegant corkscrew. The sun streaks ahead like the tip of an arrow, and the planets spiral around behind it, tracing helixes through the dark, winding around an invisible line as the whole system drills forward through the galaxy. It is genuinely beautiful to look at, and it almost always comes with a caption or a voice that says something like this: "Forget what your teachers told you." The planets do not really orbit the Sunday. That is the old idea, the wrong idea. This, the vortex, the corkscrew, this is how we really move. I want to talk about that video tonight because it is not exactly wrong, and that is what makes it so interesting. The corkscrew is real, in a sense. You could film the solar system from the right vantage point, and you would see something very much like it. But the story wrapped around the animation, the part that says the old picture is wrong, and this new picture is the truth, that part is misleading in a deep and specific way. And once you understand exactly how it is misleading, a door opens. Behind that door is the real answer to a question that sounds simple and turns out to be one of the strangest questions you can ask. How does the Earth actually move through space? How do you move through space, right now, sitting wherever you are sitting? The honest answer is that your motion through the universe is far more complicated than the corkscrew animation suggests, and far more interesting. It is not one motion. It is a nested stack of motions, layered inside one another like the workings of an old clock, and each layer turns out to teach us something specific and surprising about the universe we live in. By the end of tonight, you will have a picture of yourself moving in at least 6 different ways at once, at speeds of hundreds of kilometers per second, through a structure so large that the word large stops meaning anything. And here is the part that the meme never tells you. At the very same time, in the way that matters most for your actual life, you are also completely, perfectly still. Think for a moment about how strange it is that you do not feel any of this. You have spent your whole life on the surface of a spinning planet, and the planet has never once paused. As you read this, the patch of the Earth you are resting on is wheeling eastward. The planet beneath you is racing along its orbit around the Sunday. The Sun is hauling the entire solar system around the galaxy, and the galaxy is drifting through a sea of other galaxies. 4 separate motions at least, stacked one inside another, and not one of them registers. No wind in your face, no pressure against your back, no blur in your vision. The cup of coffee on your table sits perfectly level. A dropped key falls perfectly straight down. Every instinct you have, Every signal your body sends you insists that you are sitting still in a still room in a still world. And every one of those instincts is, in a certain precise sense, both completely correct and completely missing the point. Tonight is about that gap. The gap between the calm you feel and the dance you are part of, and about why both of them are true. Both of those things are true. That is not a contradiction to be resolved. It is the whole point. And to see why, we have to start by being very careful about a word that the corkscrew video uses without ever examining it. The word is really. They say, this is how we really move. Before we can talk about how you move, we have to talk about what that word is quietly hiding. So here is the trouble with the vortex. The animation does not just show you the corkscrew. It tells you the corkscrew is the true motion, the real motion, and that the familiar picture of planets circling a steady sun is a lie you were told as a child. That claim contains a hidden assumption, and the hidden assumption is wrong. It assumes that there is one correct place to stand when you watch the solar system, one privileged point of view from which you see things as they truly are, and that everybody else is seeing an illusion. It assumes that the universe has a single, right answer to the question, what is moving and what is still? It does not. And the reason it does not is one of the oldest and most beautiful ideas in all of physics, an idea that is almost 400 years old, and that we are going to spend the next few minutes sitting inside. Once you have it, the vortex meme quietly falls apart in your hands, and what is left is something much better. Not a debunking, an invitation. Because the real motion of the Earth, the thing the meme was pointing at and got wrong, is genuinely awesome. It just is not a vortex. It is something stranger. Let me take you onto a ship. Part 2. The ship with the portholes closed. Imagine you are below deck on a large sailing ship. The ship is moving steadily across a perfectly smooth sea, gliding forward at a constant speed. No waves, no shudder, no sound of weather. You are inside an enclosed cabin. The portholes are closed. There is no window, no view of the water, no way to see the horizon slide past. It is just you in a sealed wooden room, and the room is, as far as you can tell, an ordinary room. Now, I want you to try to figure out, without opening anything, whether the ship is moving. You could drop a coin and watch it fall. It falls straight down to the floor, the way a coin always falls. You could pour water from one cup into another. It pours normally in a smooth arc, exactly as it would in a kitchen on dry land. If there were a bowl of water on the table, its surface would lie perfectly flat and level. If there were flies or butterflies in the cabin, they would drift around in lazy loops, going nowhere in particular, not piling up against the back wall. You could throw a ball to a friend across the room, and the throw would feel completely normal. You could jump straight up in the air, and you would come straight back down to the same spot on the floor, not landing somewhere behind you as if the room had slid out from under your feet. Every single experiment you try gives you the answer that you are standing still in an ordinary, motionless room, and yet the ship might be racing across the sea at the speed of a galloping horse. There is, from inside that sealed cabin, no experiment you can perform, none at all, that will tell you whether the ship is gliding forward at a steady speed or sitting perfectly still at anchor. Stay inside that cabin for a moment longer, because the feeling of it matters. It is a quiet room. The timbers creak softly the way old wood does, and that creak would sound exactly the same whether the ship were moving or moored. The light through the closed portholes is dim and even. If you set a marble down on the flat tabletop, it sits where you placed it. It does not roll toward the back of the room as though the floor were tilting away beneath it. If you light a candle, the flame stands straight up, steady, not streaming backward as it would in a wind. Everything in the cabin behaves with a perfect, ordinary calm. And the unsettling thing, the thing Galileo wanted you to feel, is that this perfect, ordinary calm is not evidence of anything. It is not telling you that you are still. It would look precisely, identically, the same if the ship were carving across the sea faster than any horse could run. The calm is real. It is just not the kind of fact you thought it was. This thought experiment is not mine. It belongs to Galileo Galilei, and he described it in a book he published in the year 1632, a book called Dialogue Concerning the Two Chief World Systems. He used the sealed cabin to make a point that, at the time, was revolutionary, and that remains, 400 years later, one of the load-bearing pillars of physics. The point is this: steady motion in a straight line is undetectable from the inside. There is no experiment that distinguishes being at rest from moving at a constant speed. And if no experiment can tell the difference, then physics itself does not distinguish between them. As far as the laws of nature are concerned, the moving cabin and the still cabin are the same thing. We have a name for the deeper idea that grows out of this. We call it Galilean relativity. And the heart of it is a claim that sounds modest and turns out to be enormous. There is no such thing as absolute rest. There is no single, special, privileged place in the universe that is truly motionless, against which everything else can be measured as moving. The universe does not come with a fixed background grid, a cosmic floor, a still point that everything else moves relative to. Every frame of reference that is not accelerating, every steadily moving viewpoint, what physicists call an inertial frame, is exactly as valid as every other one. From inside any of them, you are entitled to say you are the one standing still and everything else is moving. And you are not wrong. Take a moment with that, because it is genuinely strange, and it does not feel true. It feels obvious that there is a difference between moving and standing still. You can feel yourself stand up and walk across a room. But notice what you are actually feeling when you do that. You are feeling acceleration, the change of motion, the push as you speed up, and the pull as you slow down. That you can detect. Acceleration is real and physical, and your inner ear will tell you about it whether you want to know or not. But steady, constant, unchanging motion, the glide of the ship across the smooth sea that you cannot feel and cannot measure from the inside. And the universe agrees with you that there is nothing there to measure. Now look back at the corkscrew video with Galileo standing next to you. The vortex animation shows you the solar system from one particular viewpoint, a viewpoint roughly fixed to the galaxy, and from that viewpoint, yes, the planets trace helixes. That is a real and valid thing to see. But the meme then makes a leap. It says that because the helix looks more dramatic, more dynamic, more like real motion, it must be the true picture, and the calm classroom diagram of planets circling a sun must be the false one. That leap is the mistake. It is choosing one frame of reference and crowning it king, declaring that the view from the galaxy is reality and the view from the sun is a lie. I want to give that mistake a name, because naming it makes it easy to spot, and once you can spot it, you will see it everywhere. Let us call it reference frame chauvinism. It is the belief that one point of view is privileged, that one frame is the real one and the others are illusions, when physics says clearly and firmly that no such privileged frame exists. The corkscrew is not more true than the classroom diagram. The classroom diagram, the planets serenely orbiting the sun, is a completely valid and correct description of the solar system. The corkscrew is also a completely valid and correct description. They are the same physics, the same planets, the same gravity, simply watched from two different chairs. Neither chair is the throne. And here is the small, quiet, slightly unsettling thing to carry forward from Galileo's sealed cabin. You are in one right now. The room you are in, the bed or the chair, the floor beneath it, the walls around it, the portholes are closed. You cannot feel the motion of the earth, or the sun, or the galaxy, any more than the traveller in the cabin can feel the ship. You have spent your entire life inside a sealed cabin, gliding across a smooth sea, and the calm of the room around you is not telling you that you are still. It is only telling you that, whatever you are doing it steadily. Hold on to that. We are going to come back to that sealed cabin at the very end, and when we do, it will mean something different than it does right now. Part 3. Choosing the useful frame. If there is no privileged frame of reference, no true viewpoint, you might think the question we started with has just dissolved. If every frame is equally valid, then asking how the Earth really moves seems meaningless, because really has lost its anchor. There is no really. There is only a menu of equally true descriptions. But that is not quite where Galileo leaves us, and it is important to be precise here, because this is the hinge the whole rest of the night turns on. Galilean relativity tells us there is no single, fundamentally correct frame of reference. It does not tell us that all frames are equally useful. Those are very different statements. The universe does not hand us one true answer, but it absolutely does let us choose a good answer, and the skill, the actual physics, is in choosing well. We do not look for the true frame, we look for the useful frame, the one that makes the question we are asking simple to answer. You do this constantly, without ever noticing. Think about catching a ball. Someone throws a ball toward you, and your brain, somewhere below the level of conscious thought, computes its arc, predicts where it will come down, and sends your hand to meet it. To do that calculation, your brain treats the ground you are standing on as a fixed, motionless stage. It does not, and should not, take into account the fact that the surface of the Earth beneath your feet is sweeping eastward at something like 1,000 kilometers per hour as the planet rotates. For the 2 seconds the ball is in the air, the patch of ground you are standing on is a perfectly good motionless frame, and treating it that way gives you the catch. If your brain tried to do that calculation in a frame that honestly accounted for the Earth's rotation, the orbit around the Sun, the motion through the galaxy, you would never catch anything. You would be paralyzed by arithmetic. The local ground is not the true frame. It is the useful frame, and using it is the right thing to do. Move the scale up. Suppose you work at a space agency, and your job is to send a robotic spacecraft to Mars. Now the rotating Earth is no longer something you can ignore, and neither is the Earth's orbit around the Sunday. But you also would not choose the frame of the launch pad in Florida to plan that journey, and you would not even choose a frame fixed to the center of the Earth. You would choose a frame fixed to the solar system as a whole, an inertial frame in which the Sun sits roughly at the middle and the planets move in their stately ellipses. In that frame, the celestial mechanics of getting a spacecraft from one moving planet to another moving planet becomes a clean, solvable problem. And in that frame, you happily, deliberately ignore the fact that the entire solar system, the Sun and Mars, and your spacecraft, and everything else, is sweeping around the center of the galaxy at hundreds of kilometers per second. For the purpose of a trip to Mars, the galaxy's motion simply does not matter. You leave it out. Not because it is false, but because it is not useful. Notice that this is not a trick, and not a compromise, and not an approximation you should feel slightly guilty about. It is the correct way to do physics. The space agency engineer who ignores the galaxy is not making an error that a more careful engineer would catch. The galaxy's motion genuinely does not affect the trajectory from Earth to Mars in any way that matters, because the Earth, Mars, the Sun, the spacecraft, and the engineer are all being carried around the galaxy together, all in the same sealed cabin, and motion shared by everything in the cabin cannot change what happens inside it. That is Galileo's principle again, doing real work. The shared galactic motion is invisible to the problem precisely because it is shared, so the engineer is not cutting a corner. The engineer is choosing the frame in which the unimportant motion drops out, and only the important motion remains. That is the whole art. And it means that when we ask how the Earth really moves, we are not going to get one number, because there is no one frame. We are going to get a layered answer, a different motion visible in each well-chosen frame and every layer of it real. You do this constantly in ordinary life too, far below the level of physics, and noticing it makes the idea feel less abstract. When you walk down the aisle of a moving train, you naturally think of yourself as moving, and the seats as still, even though, from the ground outside, the seats are hurtling along at speed and you are barely faster than they are. When you watch, the moon seems to race through the clouds on a windy night. You know perfectly well it is the clouds that are moving and the moon that is nearly fixed, even though your eye is given the opposite story. Your mind is forever choosing which thing to call still and which thing to call moving, choosing the frame that makes the scene make sense, and most of the time it chooses so smoothly that you never catch it deciding. Physics is simply doing that same thing, deliberately, carefully, and out loud. It is choosing the frame on purpose and admitting that it has chosen. So the question, how does the Earth really move, does have an answer, a rich and real answer, but it is not a single answer. It is a sequence of answers. To get it, we are going to do exactly what the space agency does. We are going to pick frames of reference, one after another, deliberately, each one chosen, because it is the most useful frame for seeing one particular layer of your motion. We will start close to home, in the frame of the solar system, and we will ask how the Earth moves there. Then we will step outward to the frame of the galaxy and ask the question again. Then outward again, to the scale of galaxies and clusters of galaxies. And at each step, the motion we uncover will not just be a number, it will be a window. The way the Earth moves at each scale turns out to reveal something about how the universe is built at that scale. The motion is not just motion, it is information. That is the method. Choose the useful frame, look at the motion it reveals, and read what that motion is telling us. Let us choose the first one. Let us start, as the meme does, with the solar system. But we are going to find that even here, in the most familiar territory there is, the classroom picture you were given is hiding something. Part 4. The sun was never standing still. Picture the solar system the way you were taught to picture it. The sun sits in the center, fixed, steady, the great anchor of the whole arrangement. Around it, the planets move in their orbits, Mercury close and quick, then Venus, then Earth, then Mars, and out beyond them the giants Jupiter and Saturn, and the cold, distant worlds past those. It is a clean and lovely picture, and for almost everything you would ever want to do, it is correct. But there is one specific thing about it that is not quite right, and the wrong part is the very center. It is the idea that the sun is fixed. The sun is not fixed. The sun moves. And it moves for a reason that, once you hear it, is obvious, and yet it is left out of almost every diagram. Gravity is mutual. When we say the sun's gravity holds the Earth in orbit, we are telling half the story. The sun pulls on the Earth, yes, but the Earth pulls on the sun with exactly as much force at exactly the same instant. Gravity is never a one-way grip. It is always a two-way bond. Every planet in the solar system is tugging on the sun all the time, and the sun feels those tugs and responds to them by moving. Now, the Earth's tug on the sun is gentle because the Earth is small. But the solar system contains two objects that are not small at all. Jupiter is a giant, more massive than all the other planets put together, and Saturn is the second giant. And those two worlds pull on the sun hard enough to genuinely move it around. To describe this properly, we need to choose our frame of reference carefully, the way we promised. And the right frame here is not a frame fixed to the Sunday. The right frame is fixed to a point called the barycenter. The barycenter is the center of mass of the entire solar system, the single balance point of all that matter taken together. And it is the barycenter, not the sun, that is the true still point of the solar system. Everything in the solar system orbits the barycenter. The planets orbit it, and the sun orbits it too. Where is this barycenter? It moves around because it depends on where the planets are, and the planets are always moving. Its location is dominated by the two giants, Jupiter and Saturn, because they carry the most weight in the balance. When Jupiter and Saturn happen to be on opposite sides of the Sun, their pulls partly cancel, and the barycenter sits deep inside the Sun, somewhere beneath its glowing surface. But when Jupiter and Saturn swing around to roughly the same side of the Sun, lining up and pulling together, the barycenter gets dragged outward, and it can end up well outside the Sun entirely, hanging in empty space beyond the Sun's surface. So picture it now from the barycenter's point of view, which is the useful frame. From here, the Sun is not the still king at the center. The Sun is performing a slow, looping, continuous dance. It traces out a complicated wandering path, a kind of pirouette, never straying far, but never truly resting either. It is choreographed almost entirely by Jupiter and Saturn, the two heavy partners, and it has the rhythm of their years. Jupiter takes about 12 Earth years to go around once. Saturn takes about 29. And so, the Sun's little dance plays out on those timescales. A 12-year sway crossed with a 29-year sway, the Sun forever circling a point that is sometimes inside it and sometimes outside it. It is worth pausing on how counterintuitive this is, because the mind resists it. The Sun contains more than 99% of all the mass in the solar system. Every planet, every moon, every asteroid and comet, all of them together, add up to less than 1% of the whole. It feels as though something that overwhelmingly massive should simply sit still, unmoved, while the small things scurry around it. But mass does not buy stillness. Mass only buys a smaller response. The Sun does respond to Jupiter's pull, exactly as Jupiter responds to the Sun's pull, with one and the same force between them. The Sun just responds less, moves less, because it is so much heavier. The pirouette the Sun traces around the barycenter is small. Compared to the orbits of the planets, it is a modest little loop. But it is not zero. And the difference between small and zero here is the difference between a diagram that is slightly wrong and a picture that is honest. The Sun moves. Heavy things still move. The heaviest object for light years in any direction is, quietly, perpetually, dancing. This already overturns the picture, the meme attacked, but in the opposite direction from the meme. The corkscrew video says the classroom picture is wrong because it shows planets orbiting a Sunday, but the classroom picture is not wrong for showing orbits. It is slightly wrong for showing the Sun as motionless. Even here, at the smallest and most familiar scale, before we have left the solar system at all, the Earth's motion is already more intricate than the diagram. The Earth does not orbit a fixed Sunday. The Earth orbits the barycenter, and the Sun orbits the barycenter too, the two of them moving in a linked, mutual dance, with all the other planets joining in. And the Earth's orbit itself is not the fixed, frozen ellipse of the diagram. Because the barycenter is slowly shifting around, and because the other planets are constantly adding their own small gravitational tugs, the Earth's orbit is gently, endlessly worked on. Its elliptical shape stretches and squishes very slightly, becoming a little more elongated and then a little more circular and back again, on the rhythm of Jupiter's and Saturn's years. And the whole ellipse slowly rotates, its long axis swinging around the Sun, not quickly, but steadily, over many thousands of years. The Earth's orbit is not a track laid down once and travelled forever. It is a living shape. It breathes. It turns. This matters more than it might sound, because these slow changes in the Earth's orbit have a name and a consequence. Together with a slow wobble in the tilt of the Earth's axis, the changes in the shape and orientation of the orbit make up what are called the Milankovitch cycles. And the Milankovitch cycles are tied to one of the great rhythms of our planet's history. They are connected to the timing of the ice ages, the long, slow advances and retreats of the great glaciers, the cycle that carved the lakes and valleys of the northern world and shaped where our own ancestors could live and travel and survive. The advance and retreat of mile-thick ice across continents is paced, in part, by the slow breathing of the Earth's orbit. And the Earth's orbit breathes because the Sun is not standing still, because Jupiter and Saturn are pulling it into its slow pirouette, because gravity is mutual and there is no fixed center after all. So we have our first layer, and already the lesson of the night is showing itself. We looked at the most familiar motion there is, the Earth going around the Sun, and we found that it was not what the diagram said. The Sun moves, the orbit breathes. And the deep climate history of our planet, the ice that shaped the human world, is written into that motion. We chose the useful frame, the barycenter, and the motion it revealed told us something real. And notice, before we go on, that nothing we just uncovered makes the classroom diagram a lie. The diagram of planets circling a sun is still a perfectly good picture for almost every purpose you could have. If you want to know when the next eclipse falls, or how the seasons turn, or where Jupiter will be in the night sky next month, the simple picture serves you completely. The barycenter, the breathing orbit, the slow precession, these are not corrections that overturn the diagram. They are a finer layer beneath it, visible only when you choose the frame that brings them into focus. That is how this whole night is going to go. We are not knocking down one picture to put up a truer one. We are adding layer beneath layer, each one real, each one visible from its own well-chosen frame, none of them cancelling the others. Now, let us choose the next frame and step outward, because the solar system, for all its quiet intricacy, is about to look very small. Part 5. 230 kilometers per second. We have been treating the solar system as a self-contained thing, a sun and its planets dancing around a balance point. But the solar system is not alone, and it is not still. It sits inside something vastly larger, a great wheeling city of stars, and that city is the Milky Way galaxy. To see the next layer of your motion, we have to leave the solar system frame behind and choose a new one, a frame fixed to the galaxy itself. And immediately the problem gets harder. Inside the solar system, working out how things move is, relatively speaking, manageable. There are only a handful of bodies whose gravity really matters, and over all of them looms the Sun, which carries the overwhelming majority of the mass. The gravity of the solar system is, to good approximation, just the gravity of the Sun, with small corrections. That is a tractable problem. You can hold it in your head. The galaxy is nothing like that. The Milky Way's gravity is not dominated by a single object. There is no central mass that holds the rest the way the Sun holds the planets. Instead, the galaxy's gravitational field is the summed pull of everything it contains, hundreds of billions of stars, vast clouds of gas and dust, and a great invisible halo of dark matter, all of it pulling on all the rest. Every star in the Milky Way moves in the combined gravity of every other star and everything else besides. There is no king. There is only the crowd. That makes the motion fiendishly hard to calculate. But, and this is the gift hidden inside the difficulty, it also makes the motion enormously informative. Because every star is moving in the summed gravity of the whole galaxy, the way the stars move is a readout of how the galaxy's mass is arranged. Watch the stars carefully enough, track their motions precisely enough, and you can reconstruct the structure of the galaxy itself, including the parts you cannot see. The motion is, once again, information. We will lean on that hard before the night is over. For now, the headline number. The solar system, the whole thing, sun and planets and all, is moving around the center of the Milky Way at a speed of roughly 230 kilometers per second. 230 kilometers every second. In the time it takes to read this sentence aloud, you and the Earth and the Sun have traveled something like 1,000 kilometers along the galactic orbit. It is a genuinely enormous speed, and you feel none of it, because, of course, you are in Galileo's sealed cabin, gliding steadily, and steady motion cannot be felt. But here is the thing that makes the galactic scale land in the body, and it is not the speed, it is the time. The galaxy is so vast that even at 230 kilometers per second, a single trip around it, one galactic orbit, one galactic year, takes nearly 230 million years. Let that number settle, because it is hard to hold. 230 million years for one lap. Imagine standing at the Sun's current position in the galaxy and looking back along the orbit, back to the last time the solar system was right here in this same stretch of the Milky Way. That was 230 million years ago, and the Earth of 230 million years ago is not a place you would recognize. There was a single supercontinent then, the great landmass we call Pangaea, still assembled, its pieces not yet torn apart, into the continents we know. Dinosaurs walked that supercontinent, early ones, in a world that had only recently survived the largest mass extinction in the planet's history, the one that had wiped out the trilobites and so much else. The last time the solar system occupied this exact patch of the galaxy, the entire age of the dinosaurs had not yet happened. It would unfold, all of it, every species you can name, and 1,000 you cannot, the whole long reign, and it would end, and the mammals would rise, and the primates, and eventually us, and we would build cities and telescopes and look up, all of it, in the time it has taken the Sun to come around the galaxy just once. And the solar system has been alive for about 4.5 billion years, which means that in its entire existence, from its birth out of a collapsing cloud of gas to this very moment, the Sun has completed only about 20 laps of the galaxy. 20. The solar system is roughly 20 galactic years old. A human lifetime, against that clock, is not even a flicker, it is nothing. You could not live long enough to see the Sun's galactic position shift by any amount your eye could register. Stay here a moment, in this thought, because it is one worth lying still inside of. Imagine you could stand outside the galaxy, far above the great glowing wheel of it, and watch the solar system move. You would have to be impossibly patient. At human speeds of attention, nothing happens at all. The Sun simply hangs there among its neighbor stars, fixed, eternal. To see it move, you would have to let centuries pass between blinks. Let 1,000 years go by, and the Sun has shifted by a small amount, a step along the great orbit. Let 100,000 years go by, and it has travelled a noticeable arc, and yet it has not even begun the journey. To watch the Sun complete one single circuit of the galaxy, you would have to sit and watch for 230 million years without looking away. And in that one circuit, that one slow turn of the great wheel, the entire age of the dinosaurs would rise and fall. Whole mountain ranges would be lifted up out of the earth and worn back down to nothing. Oceans would open and close. The continents themselves would drift into new arrangements and drift on again. And the Sun, through all of it, would simply be coming around once, one lap. The galaxy keeps a kind of time that has nothing to do with us, a slow and enormous time, and we are passing through a single, quiet instant of it tonight. And so is everyone we have ever known, and so was every human being who has ever lived, all of us together inside one shared blink of the galactic year. This is the slow, vast, patient motion that the corkscrew meme is gesturing at, and it is real, and it is awesome, and it deserves better than a vortex. But before we can see its true shape, we need a tool. We need a way to describe the Sun's galactic motion precisely, and to do that, we need, once again, to choose a frame of reference. And the frame we choose here is one of the cleverest ideas in galactic astronomy, because it is a frame built not out of a real object, but out of an idealized, perfect, imaginary orbit. The trouble is this. To describe the sun's motion through the galaxy, you might think we should just measure it relative to the center of the galaxy. But the galactic center is a difficult thing to pin down precisely and an awkward thing to measure against. So astronomers do something subtler. Instead of measuring the sun against the galactic center, they measure it against a hypothetical orbit, a perfect circular orbit passing through the sun's current location. They imagine an idealized point that sits exactly where the sun is now, but that is moving on a flawless circle around the galaxy, never wobbling, never drifting, just sweeping out a perfect circular path. That imaginary, perfectly circular reference orbit has a name. It is called the local standard of rest. And the local standard of rest is wonderful, because once you have it, you can describe the sun's real motion not in absolute terms, but as a departure from perfection. You can ask, how does the sun's actual motion differ from that flawless circle? How not circular is the sun's orbit, and in which directions? There is even a good physical reason this idealized circle is the right baseline, and not just a mathematical convenience. It turns out that nearly every star in the disk of the Milky Way begins its life on an orbit that is very close to a perfect circle. Stars are born from great clouds of gas, and gas, unlike stars, experiences friction. A cloud of gas drifting through the galaxy bumps and rubs against other gas, and that friction smooths out its motion, nudging it onto a nice circular orbit, the way friction smooths and settles almost everything. So, when a new star condenses out of such a cloud, it is born already moving on the circular orbit. Its birth cloud had been friction smoothed into. It starts life on the ideal circle, but then the star grows up, and a star, unlike the gas it was born from, feels no friction. Nothing smooths its motion anymore. Instead, over millions and hundreds of millions of years, the star gets jostled. It passes near other stars, near massive clouds, near the great spiral arms, and each close encounter gives it a small gravitational kick. The kicks add up. Slowly, gradually, the star is nudged off its perfect birth circle onto a more complicated, less circular path. It accumulates a personal history of every gravitational encounter it has ever had, written into the shape of its orbit. And that gives astronomers a beautiful way to actually measure the local standard of rest. To find that idealized circular motion, you go looking for the youngest stars you can find, the ones that were born recently and have not yet had time to be kicked around, the ones still riding close to their birth circles. You gather many of them and average their motions, and that average gives you the circle, the local standard of rest, and then you can compare the sun to it. When you do that, when you finally measure the sun against the perfect circle, you discover that the sun is not on the perfect circle at all. The sun has its own small particular departure from the ideal, its own personal deviation, built up over 4.5 billion years of gravitational kicks. Astronomers call that deviation the sun's peculiar motion, and the word peculiar here does not mean strange. It means particular, specific, the sun's own. The peculiar motion is small, just a handful of kilometers per second against the 230 of the main orbit. But it is not nothing. It is, in fact, the key to the next several layers of the story, and it has consequences that are anything but small. Part 6. The flower the sun is drawing. So the sun is not riding the perfect circle. It has a peculiar motion, a small particular drift of its own, and to understand the real shape of our path through the galaxy, we need to look at that drift closely. It has 3 parts, 3 directions, and we can take them one at a time. First, the sun is drifting forward. Along the direction of the galaxy's rotation, the direction the whole great wheel of stars is turning, the Sun is moving slightly faster than the idealized circle would carry it. The extra speed is about 5 kilometers per second. The Sun is, you might say, very gently overtaking the perfect circle, easing ahead of where a flawless circular orbit would have placed it. Second, the Sun is drifting inward. Toward the center of the galaxy, toward the distant core, the Sun is moving at about 8 kilometers per second. It is, right now, slowly closing the distance between itself and the galactic center. And third, the Sun is drifting upward. Out of the flat plane of the galaxy's disk, rising up out of the great pancake of stars, the Sun is moving at about 7 kilometers per second, 3 small drifts. 5 kilometers per second forward, 8 kilometers per second inward, 7 kilometers per second upward. Set against the 230 kilometers per second of the main orbit, these are tiny corrections, a few percent. But each one of them shapes the path in ways that matter, and the first thing we should do is calm a fear that the second number might have raised. The Sun is drifting inward toward the galactic center at 8 kilometers per second. At the center of the galaxy, there is a supermassive black hole, an object of more than 4 million times the mass of the Sun, called Sagittarius A star. So you might reasonably wonder whether this inward drift is the beginning of a long fall, whether the solar system is slowly spiraling down toward that black hole, doomed to eventually arrive. It is not. We are in no danger of falling into Sagittarius A star, and the reason is worth understanding because it leads straight to the real shape of our galactic path. The Sun's inward drift is not a fall. It is simply the inward part of a slightly off-circular orbit. The Sun is on a galactic orbit that is not a perfect circle, but a little bit elliptical, a little bit stretched. And right now the Sun happens to be on the part of that not quite circular orbit that carries it gradually nearer the center. Later, it will be on the part that carries it gradually back out. It is moving in, and then it will move out, the way a planet on an elliptical orbit moves nearer its star and then farther away. There is no spiral of doom. There is just an orbit that is not a perfect circle. But here is where it gets genuinely beautiful, and here is where we finally meet the real shape of our motion, the shape the corkscrew meme was reaching for and missing. The Sun's galactic orbit is not a simple ellipse either. It cannot be, and the reason it cannot be takes us back to the difference between the solar system and the galaxy. In the solar system, almost all the mass is concentrated in one place, in the Sun, sitting at the middle. And when mass is concentrated like that, at a central point, orbits around it are simple closed ellipses. A planet goes around, comes back exactly to where it started, and retraces the same ellipse forever. That is the orbit of the Earth around the Sunday. It closes, it repeats. The galaxy is not built that way. The galaxy's mass is not concentrated at the center. It is spread out, smeared through the entire enormous volume of the disk and the halo, stars and gas and dark matter, distributed across 100,000 light years. And when the mass that is pulling on you is spread out like that, instead of concentrated at a point, the orbits change their character entirely. They no longer close. A star going around the galaxy does not come back exactly to where it started. Each loop around is slightly offset from the loop before it. The orbit advances, turns, never quite repeating, and over many loops it traces out a pattern, and the pattern it traces is a flower. Loop after loop, each one rotated a little from the last, the orbit fills in a great rosette, a flower-petal pattern, petal after petal, sweeping out around the galactic center, the whole figure slowly turning. The geometers have a word for this kind of motion. They call it epicyclic, and the classic image of an epicyclic curve is the looping pattern that a small wheel traces when it rolls around the rim of a larger wheel, a curve that loops and loops and never closes on itself, slowly drawing a rosette. That is the shape of the solar system's path through the galaxy, not a circle, not an ellipse. A slowly turning flower, an unclosing rosette of petals drawn at 230 kilometers per second across hundreds of millions of years. It is worth noticing that this difference between a closed ellipse and an unclosing rosette comes entirely from how the mass is arranged and nothing else. Same gravity, same law. In the solar system, the mass is gathered into a point, the sun, and gravity around a point gives you orbits that close, that repeat, that come home. In the galaxy, the mass is spread through a vast volume, and gravity through spread out mass gives you orbits that never quite close, that always advance, that draw flowers instead of circles. The geometry of your path is a direct readout of how the matter around you is distributed. Walk close to home and you orbit a point and your path repeats. Walk out into the galaxy and you orbit a cloud and your path blooms. The same falling, the same gravity, just listening to a different arrangement of mass and answering with a different shape. And now look back at the corkscrew meme one more time, because here, at last, we can be fair to it. The meme was not wrong to sense that there was looping motion, that there was structure, that the path of the solar system through the galaxy was something richer and more intricate than a flat diagram of circles. There is looping, there is structure, there is real geometric beauty in our path. The meme's instinct was right. It was the meme's specific picture that was wrong. The truth is not a corkscrew dragged stiffly behind a speeding Sunday. The truth is a flower, drawn slowly, petal by petal, over a span of time so long that the human mind can barely touch it. There is one more consequence of the flower worth sitting with, quietly, because it is the kind of fact that changes how the next clear night feels. Because the orbit never closes, because each petal is offset from the last, the Earth has never once retraced its own path through the galaxy. Not ever. In 4.5 billion years of motion, across 20 laps of the Milky Way, the Earth has never returned to a point in the galaxy it has occupied before. Every position the Earth has ever held in the galaxy, it held once, and then moved on, and will never hold again. And the place you are right now, this exact location in the Great Rosette, the Earth is passing through for the first and only time in the history of the solar system. You are, in the most literal geometric sense, somewhere genuinely new. You will never be here again, and neither will the planet beneath you. It is gentle, this fact, not frightening, and I want to leave it gentle. There is a version of never returning that sounds like loss, and that is not the version that is true here. The Earth is not lost. It is simply always arriving. Every night you have ever spent on this planet, you spent it in a place the Earth had never been before and would never be again, and you did not feel any poorer for it. The flower the sun is drawing is not a cage, and not a track worn smooth by repetition. It is an open, unrepeating line, always reaching into galaxy it has not yet touched. And there is a kind of quiet privilege in that, in being carried, without effort, without even noticing, into a piece of the universe that is genuinely new. You do not have to do anything to be an explorer. You already are one. You have been one your whole life, simply by lying still on a planet that never stops arriving somewhere. Part 7. The long, slow bob through the disk. We have looked at two of the sun's three small drifts. The forward drift, easing ahead of the perfect circle. The inward drift, carrying us nearer the galactic center on a gently off-circular orbit. Now we come to the third drift, the upward one, and it is the smallest of the three and by far the most consequential. The sun is rising out of the galactic disk at about 7 kilometers per second, and that gentle rise turns out to set a clock that may have governed the history of life on Earth. Start with the geography. The Milky Way, seen edge-on, is shaped like a vast flattened disk, a great glowing pancake of stars, far wider than it is thick. There is a central plane running through the middle of that pancake, the midplane of the disk, where the density of stars and gas is greatest, and the Sun does not sit exactly on that midplane. Right now, the Sun is a little above it, somewhere in the range of a few dozen light-years above the central plane of the galaxy, and it is moving upward, away from the midplane, at that 7 kilometers per second. I should be honest with you about a difficulty here, because it is the kind of difficulty that is itself interesting. It is genuinely hard to say exactly where the midplane of the galaxy is. The disk is not a sheet of paper with a crisp center line. It is a soft, fuzzy, dynamic distribution of billions of stars and great drifting clouds of gas, and the midplane is a statistical feature of that fuzz, an average, not a sharp surface. So when astronomers say the Sun is a few dozen light-years above the midplane, there is real uncertainty wrapped around that statement. The galaxy does not come with a painted center line. We are inferring where the middle is from the crowd. But the upward motion is real, and the question it raises is obvious. If the Sun is rising out of the disk, where does it go? Is it leaving the galaxy? It is not. The Sun is not escaping. And the reason is gravity, working exactly the way you would hope. As the Sun rises above the midplane, it leaves more and more of the galaxy's matter below it and less above it. The great mass of the disk is now beneath the Sun's feet, so to speak, and it pulls. The disk's gravity reaches up and steadily slows the Sun's rise, the way the Earth's gravity slows a ball you have thrown straight up into the air. The Sun climbs, but it climbs against a pull, and it climbs ever more slowly. In a few million years, the Sun's upward motion will slow all the way to a stop. By then it will have risen to something like 300 light-years above the midplane, the top of its climb, the highest point it will reach. And there, for a moment, it will hang, motionless in the vertical direction. And then it will begin to fall. It will fall back down toward the disk, gathering speed as the disk's gravity pulls it in faster and faster, until it plunges through the crowded midplane at its greatest vertical speed. And it will not stop there. It will overshoot, shooting straight through the midplane and out the other side, down below the disk now, rising away from the midplane in the opposite direction, slowing again as the disk's gravity once more takes hold until it reaches the bottom of its travel, 300 light-years below the plane this time, hangs again and falls back up. It is the same motion, in its essence, as a marble rolling back and forth in the bottom of a bowl, or a pendulum swinging through the lowest point of its arc, the disk's gravity playing the part of the bowl, always pulling the Sun back toward the middle, and the Sun always overshooting the middle and climbing out the far side before it is drawn back again. This is a bob, a slow, stately, vertical oscillation, the Sun rising above the disk and sinking below it, and rising again, bouncing through the galactic plane like a slow weight on a long spring. And one full cycle of that bob, up through the disk and down through the disk and back to the start, takes roughly 60 million years. Imagine riding it. Imagine you could sit with the solar system, in no hurry at all, and feel the bob the way you might feel the slow rise and fall of a small boat on a long ocean swell. Right now, you are above the midplane and still rising, but the rise is gentle and getting gentler, the disk's gravity reaching up and easing the climb. You drift higher. The stars around you thin out a little, because you are leaving the crowded middle layer of the galaxy and moving into its quieter heights. The climb slows and slows, and then, so softly you could not name the moment it happened, the rising stops. You hang there at the top, 300 light-years above the great plane of the galaxy, the whole luminous disk spread out below you, like a city seen from a hilltop at night. And then you begin, just as softly, to come back down. The fall is slow at first and then less slow, the disk drawing you in, the stars thickening around you again as you sink back toward the crowded middle, until you sweep down through the midplane at the bottom of the swing, moving your fastest, and shoot straight on through it and out the underside, and the whole long patient motion begins again, inverted, up and over and down and through and up again. 60 million years for one full breath of it. You would have to be more patient than any living thing has ever been to feel a single cycle. And yet, the solar system is doing it right now, and you are riding it right now, rising or falling through the disk of the galaxy at this very moment, and you cannot tell which. Set that against the galactic orbit. One trip around the galaxy is about 230 million years. One vertical bob is about 60 million years. So, as the solar system makes its one great lap around the Milky Way, drawing its slow flower, it also bobs up and down through the disk several times, perhaps 3 or 4 times per lap. Our path is not just the flower. It is the flower with a slow vertical wave running through it, the solar system rising and plunging through the galactic plane again and again as it circles. Now, why does this matter? Why is the smallest of the 3 drifts the most consequential? Because that 60 million year clock may be connected to something written into the rocks of our own planet. Some astronomers have proposed that the Sun's vertical bob through the disk could be linked to the timing of mass extinctions on Earth. The idea runs like this. The midplane of the galaxy, the crowded central layer the Sun plunges through, is a more dangerous neighborhood than the quiet heights above and below it. Down in the midplane, the stars are packed more densely, and there is more gas and more dust. A denser neighborhood means a higher chance of a nearby star ending its life as a supernova close enough to matter. It means a higher chance of a close gravitational encounter with some massive passing object, an encounter that could reach into the outer solar system and disturb the great cloud of icy bodies that orbits far from the Sun, flinging some of them inward on long plunging paths that might end at the Earth. The proposal is that every time the solar system passes through the crowded midplane, the danger to the Earth ticks upward, and that this rhythm, every 60 million years or so, might show up in the fossil record as a rough periodicity in the great extinctions, the moments when large fractions of life on Earth were wiped away. I want to be careful and honest here, because this is exactly the kind of idea that is easy to oversell. It is a real hypothesis, raised seriously by real astronomers, and it is also genuinely disputed. Whether the extinction record actually shows a clean 60 million year rhythm is contested. The statistics are difficult, the dating of ancient extinctions is uncertain, and not everyone is convinced the periodicity is real rather than an illusion read into noisy data. So I am not telling you that the dinosaurs died because the solar system was passing through the galactic plane. The most famous extinction, the one that ended the long reign of the dinosaurs, happened about 66 million years ago, and its immediate cause, an asteroid impact, is well established. What I am telling you is that there is a serious, unresolved scientific question about whether the slow geometry of our galactic motion, this 60 million year bob, leaves a fingerprint on the history of life. It is a question, not an answer. But sit for a moment with the shape of the question, because even as an open question, it is staggering. It asks whether the rise and fall of whole categories of life on this planet, the appearance and disappearance of entire worlds of creatures, might keep time with a clock, set not by anything on Earth, not by biology or climate or chance, but by pure geometry, by the slow bob of the solar system through the plane of the galaxy. If the idea is right, even in part, then the largest rhythms of life and death in the history of the Earth are not really earthly rhythms at all. They are galactic ones. And the same slow vertical motion that you are part of right now, rising out of the disk at 7 kilometers per second, would be one of the deepest clocks the living world has ever danced to. This is the kind of idea Sundown science loves to sit with, precisely because it lives in that honest middle ground between proven and disproven. It would be easy and wrong to tell you flatly that the dinosaurs died because of the galactic plane, and it would be just as easy and just as incurious to wave the whole notion away. The truthful position is the more interesting one. We have a real motion, the 60 million year bob, that we are confident is happening. We have a real pattern in the rocks, the great extinctions, that we are confident occurred. And we have a genuine, unresolved scientific question about whether the first thing has any hand in the second. Holding that question open, neither swallowing it whole nor dismissing it, is not a weakness. It is what it feels like to stand at an actual edge of knowledge, where the data runs out and the honest answer is we are still finding out. Most of the most beautiful questions in science live exactly there. This is one of them, and it is enough tonight simply to know that it is there, hanging over the fossil record, unanswered, waiting. Part 8. How to weigh a galaxy by watching it bounce. The vertical bob, the slow rise and plunge of the solar system through the galactic disk, is not only a possible clock for extinctions, it is something else, something I find even more remarkable, because it turns our motion into a scientific instrument. The bob is a way to weigh the galaxy, and weighing the galaxy turns out to be a way to probe one of the deepest unsolved mysteries in all of physics, the mystery of dark matter. Let me build this carefully, because the logic is lovely. Start with dark matter itself. We have known for a long time that the galaxies do not contain enough visible matter, enough stars and gas and dust, to account for their own gravity. Galaxies rotate too fast, hold themselves together too tightly, bend light too strongly to be explained by the matter we can see. There is something else there, something that has mass and therefore gravity, but that gives off no light and absorbs no light, something we have only ever detected through the gravitational pull it exerts. We call it dark matter, and it appears to outweigh all the ordinary visible matter in the universe several times over. What it actually is, what kind of particle or object it is made of, remains genuinely unknown. It is one of the great open questions, and physics has been pressing on it hard for decades. Now here is the part that connects to our bob. The different theories of what dark matter is make different predictions about one specific property. They disagree about whether dark matter interacts with itself. In the most mainstream picture, dark matter is what physicists call collisionless. The particles of dark matter sail through one another and through everything else almost without interacting at all. They feel gravity and essentially nothing else. And because such particles never bump, never rub, never lose energy to one another, they cannot settle, they stay spread out. A galaxy's dark matter, in this picture, sits in a great puffy, roughly spherical halo, an enormous diffuse cloud enveloping the visible disk, never collapsing inward, because there is no friction to let it collapse. But there are other candidates for what dark matter might be, and some of them behave differently. Some proposed kinds of dark matter would have very weak self-interactions, a slight ability to bump and jostle against themselves, a faint force a little like friction. And if dark matter could feel even a little friction, then it could do what the gas in the galaxy does. It could lose energy and settle and flatten. Instead of staying in a puffy, spherical halo, some of it would sink down and collect into a thin sheet lying right inside the galactic disk, a dark disk hidden within the visible one. And a galaxy with a dark disk would have a heavier disk, more mass packed into that central plane than a galaxy whose dark matter stayed puffy and spread out. So the two pictures, collisionless dark matter and weakly self-interacting dark matter, make a concrete, testable difference. One predicts a lighter disk. The other predicts a heavier one with a hidden dark layer inside it. If only we could weigh the galactic disk precisely enough, we could tell them apart. We could find out whether dark matter feels friction. We could narrow down what it actually is. And this is where the bob comes back, because the vertical bob is the scale. Think about what governs how high the sun rises on each climb out of the disk. It is the disk's gravity pulling it back. A heavier disk pulls harder, A star bobbing up out of a heavier disk gets pulled back sooner and does not rise as high. A star bobbing up out of a lighter disk climbs higher before it is turned around. The maximum height a star reaches in its vertical oscillation and the speed it is moving as it crosses the midplane are set directly by how much mass is in the disk. The bob is a measurement of the disk's weight, so astronomers do exactly this. They do not just track the Sunday, they track the vertical motions of great numbers of nearby stars, measuring how fast those stars move up and down through the disk and how high they climb. And from all those bobbing stars, all those little oscillations, they reconstruct the gravity of the disk, and from the gravity, they reconstruct the mass. They weigh the galactic disk by watching the stars bounce through it, and here is the result. The careful measurement of all those vertical motions, of all those bobbing stars, has so far found no evidence of any extra hidden mass in the disk, no sign of a dark disk. The disk weighs about what the visible matter and the ordinary puffy dark halos say it should weigh, and not more, which means that, as far as this measurement can tell, dark matter is not settling into the galactic plane. It is staying puffy. It is staying spread out. And that supports the mainstream picture, the collisionless picture, the picture in which dark matter feels gravity and nothing else, and never bumps against itself at all. It is worth saying clearly that a result like this, a result of finding nothing, is not a disappointment, and it is not a failure of the experiment. In science, finding nothing is finding something. The measurement did not come back empty. It came back with a real and useful answer, and the answer was that one of the possibilities is ruled out, or at least pushed hard against. Before this kind of measurement, the dark disk was a live option, a thing dark matter genuinely might have been doing. After it, the dark disk is disfavored, and the collisionless picture stands on firmer ground. The space of what dark matter could be has been narrowed, and it was narrowed by watching stars bob. That is progress of exactly the kind that does not make headlines and matters enormously. Every time a careful measurement closes off a wrong path, the remaining paths get a little brighter, and the day that dark matter is finally identified comes a little closer. The bob of the stars did that. The bob of our own solar system is part of the data that did that. I want you to sit with what just happened in that argument, because it is the emotional center of this whole video, and it is the moment the lesson of the night turns over and shows its other face. You have spent your life, almost certainly, thinking of the Earth's motion through space as something that simply happens to you, a passive fact. The planet moves, the sun moves, the galaxy turns, and you are carried along, a passenger, with no say and no stake in any of it. That is the natural way to think about it. The motion is just scenery. But that is not what the vertical bob is. The vertical bob is being read. Scientists are watching the way the solar system, and thousands of stars like it, rise and fall through the galactic disk, and they are reading that motion the way a doctor reads a pulse, drawing from it the hidden weight of the galaxy, and, through that weight, a clue to the nature of dark matter, one of the deepest unknown things in the universe. Your motion through space is not scenery. It is not a passive fact. It is information. It is a measurement taken continuously by a galaxy-sized instrument that you are riding inside of. The bob you cannot feel is, right now, helping to answer the question of what most of the universe is made of. There is something almost tender in the method. When you look at it closely, no one can hold the galaxy on a scale. No one can reach out and weigh the disk of the Milky Way directly. The disk is 100,000 light-years across, and we are buried inside it. And yet, we want to know its mass, because its mass holds a clue to the deepest question we have. So, we found another way. We let the stars do the weighing for us. Every star that bobs through the disk is, without knowing it, performing the measurement, its rise and fall governed by exactly the mass we want to know. The galaxy weighs itself continuously in the motion of its own stars, and all we have to do is watch carefully enough to read the answer off. Our own Bob, the slow rise and fall you are part of tonight, is one entry in that vast, unwilled experiment. You are a data point. The planet you are resting on is a data point. And the experiment is running, right now, whether anyone is watching or not. That is the turn. We started the night asking how the Earth moves, as if the motion were the thing to be explained. And we are discovering that the motion is not just a thing to be explained, it is a thing that explains. Each layer of our motion, properly read, is the universe telling us about itself. And we are not done. There is another layer, and it hides another instrument, and this one keeps time with the calendar on your wall. Part 9. The speed of your birthday. So far, in talking about the galaxy, we have followed the Sunday. The sun draws the flower, the sun bobs through the disk, and the planets, we have quietly assumed, just come along for the ride. But the solar system is not a point. It is a structured object, a great flat disk of orbiting worlds, and that disk has an orientation, a way it is tilted, and the tilt turns out to matter. It is the tilt that finally explains the corkscrew, and it is the tilt that gives your birthday a speed. Here is the structure. The planets of the solar system do not orbit the sun at random angles. They orbit very nearly in a single shared plane, a great flat sheet, like marbles rolling on a tabletop. We call that sheet the ecliptic plane. The Earth orbits in it, and so do the other planets, give or take small tilts. The solar system is, to good approximation, flat. Now, that flat sheet is moving through the galaxy, carried along on the sun's 230 kilometers per second. And the question is, how is the flat sheet oriented relative to the direction it is traveling? Is it lying flat against the direction of motion, like a frisbee thrown so it stays horizontal? Is it edge-on to the motion, like a coin rolling along a table, or is it tilted somewhere in between? It is tilted in between. The ecliptic plane, the flat sheet the planets orbit in, is tilted by roughly 60 degrees relative to the direction the sun is travelling through the galaxy. Not flat on, not edge on, but at a steep slanting angle to the line of march. And that tilt, that 60-degree slant, is the real, honest origin of the corkscrew. This is the thing the meme was showing you without understanding. When you have planets going around and around in a flat sheet, and you carry that whole spinning sheet forward through space along a direction that is tilted relative to the sheet, then the path each planet traces, the combination of its circling and the forward sweep, comes out as a kind of stretched, slanted helix. A squished corkscrew. The corkscrew in the animation is not a mystical, truer-than-true vortex. It is just what circular orbits look like when you tilt the orbital plane against the direction of travel and watch from outside. It is a projection. It is geometry. The 60-degree tilt is the whole secret, and now you have it. But the tilt does something else, something subtler and lovelier, and this is where your birthday comes in. Because the planets orbit within that tilted sheet, each planet spends part of its year on the leading side of the sun, out ahead of the sun in the galactic march, and part of its year on the trailing side, lagging behind the Sunday. As the Earth goes around its orbit, it is carried first ahead of the sun, then behind it, then ahead again, once per year. For the Earth specifically, the timing works out like this. The Earth is farthest ahead of the sun, leading the march, around September, and it is farthest behind the sun, trailing, around March. Twice a year, it is level with the sun in between. And here is the consequence that matters. For half the year, the Earth's own orbital motion around the sun happens to point in roughly the same direction as the sun's galactic motion. During that half, the two speeds add together. The Earth's orbital velocity and the Sun's galactic velocity are pointing the same way, and so the Earth's total speed through the galaxy is the sum of the two. It is moving as fast as it ever moves. And that maximum, that fastest point, falls around June. Then, for the other half of the year, the Earth's orbital motion partly points against the Sun's galactic motion. During that half, the two speeds partly cancel. The Earth's orbital velocity is working against the Sun's galactic velocity, and so the Earth's total speed through the galaxy is the Sun's speed minus part of the orbital speed. The Earth is moving as slowly as it ever moves. And that minimum, that slowest point, falls around December. So the Earth speeds up and slows down once a year in a slow annual rhythm, fastest in June, slowest in December. The difference is not large compared to the great 230 kilometers per second of the galactic orbit, but it is real, and it is regular, and it means something genuinely strange and genuinely true. The month of your birthday corresponds to a particular speed of the Earth through the galaxy. If you were born in June, the planet was moving through the Milky Way about as fast as it ever does on the day you arrived. If you were born in December, it was moving about as slowly as it ever does. Your birthday has a galactic speed. It is far too small a difference to matter for anything you will ever do, anything you could ever feel. And it is large enough, as we are about to see, that physicists have built detectors and buried them deep underground, specifically to try to feel it for you. It is worth letting that settle, because it is the kind of connection that, once you see it, quietly rewires how you think about the ordinary year. We tend to think of the seasons as a purely earthly thing, a matter of sunlight and the tilt of the axis, summer and winter as local weather, and they are that. But threaded through the same calendar, hidden inside the same months, is this other thing, this galactic rhythm, completely unfelt and completely real. June is not only the month the northern half of the planet leans toward the Sunday. June is also, every single year, the month the whole Earth is leaning hardest into its motion through the galaxy. December is not only the dark and cold of the northern winter. December is also, every year, the month the Earth eases off, slows in its galactic march, drifts at its gentlest pace through the Milky Way. The year you already know, the year of birthdays and holidays and changing weather, is also, at the same time, a slow turning of the planet's galactic speed, and the two calendars are laid one on top of the other so perfectly that you have lived inside both your whole life and only ever noticed one. Part 10. The wind you cannot feel and the detector under the mountain. The Earth speeds up in June and slows down in December. That small annual rhythm, that yearly quickening and slowing of our motion through the galaxy, is the basis of one of the most ingenious experiments in all of physics. It is an experiment designed to catch dark matter, and it works by listening, not for a particle, but for the calendar. Here is the idea. Remember that dark matter, in the mainstream picture, sits in a great puffy halo enveloping the whole galaxy, the visible disk drowned inside an enormous diffuse cloud of it. If that is right, then the solar system is not travelling through empty space as it orbits the galaxy. It is travelling through the dark matter halo. It is moving through a medium, an invisible fog of dark matter particles spread thinly through all the space around us. And if you are moving through a medium, then from your point of view, the medium is moving past you. From the moving Earth's point of view, there is a wind, a dark matter wind, an unending stream of dark matter particles blowing through the solar system, through the Earth, through the walls and the floor and the chair and your own body, every second, silent, untouchable, felt by nothing. If dark matter is some kind of particle, and if it fills the halo the way we think it does, then it is passing through you right now in enormous numbers, and it leaves no trace because it barely interacts with ordinary matter at all. That is what makes it dark. That is what makes it so maddeningly hard to catch. Let yourself feel that for a moment in the quiet of wherever you are lying. The room around you seems empty. The air, the dark, the still space between you and the ceiling. All of it seems like nothing at all, like simple emptiness. But if the mainstream picture of dark matter is right, then that space is not empty, it is full. A river of dark matter is pouring through the room, through the bed, through the blanket, through your chest and your hands, and the slow beating of your heart, an endless silent current, and it has been pouring through you every second of your entire life, and through every person who has ever lived, and not one of us has ever felt the faintest breath of it. It does not push, it does not warm you, it does not so much as stir a single hair. It simply passes through, the way light passes through glass, the way a thought passes through a quiet mind, there and gone, and leaving the room exactly as it found it. And the wind is not even steady. It rises and falls with the year. Right now, as you breathe, the planet is somewhere on its orbit, leaning into that current at some particular angle, and the wind through you is a little stronger or a little weaker than it will be 6 months from now. You are standing in a weather you cannot feel, and the weather has seasons. Now go down into the rock. There is a place where people are trying to catch that wind, and to reach it you have to leave the surface of the earth behind. Picture descending into a mountain in Italy, down through a long tunnel into the body of the rock, until there is 1.5 kilometers of solid stone above your head. It is silent down there, the deep silence of being inside the earth, and it is dark in a way the surface never is. The rock overhead is not decoration, it is a shield. Up on the surface, particles from space rain down constantly, a steady, noisy shower of them, and that shower would drown out the rare, faint, almost nothing signal of a dark matter particle striking ordinary matter. So the experiment is buried, the mountain pulled over it like a blanket pulled over a sleeper, to hush the noise, to make the dark deep and quiet enough that something rarer might finally be heard. And there, under all that stone, a detector sits in the hush and waits. It is not waiting for a flash or a sound. It is waiting for a rhythm. It is waiting patiently, year after year, for the seasons of a wind that no one can feel to leave their faint mark in the dark. But here is the clever part, the part that turns the annual rhythm into a tool. How much dark matter wind blows through the earth depends on how fast the earth is moving through the halo. The faster you move through a medium, the harder the wind. It is the same reason that more rain hits the windshield of a car the faster you drive. Drive slowly through a rain shower, and the windshield catches a gentle patter. Speed up, and the same rain comes at the glass as a hard, fast drumming. You have not changed the rain. You have changed how fast you are driving into it. The earth does exactly this with the dark matter wind. In June, when the earth is moving fastest through the galaxy, it is driving hardest into the dark matter halo, and the dark matter wind blowing through it is at its strongest. In December, when the earth is moving slowest, it is driving most gently into the halo, and the wind is at its weakest. So if you built a detector sensitive enough to register the occasional rare interaction of a dark matter particle with ordinary matter, that detector should see more events in June than in December. The signal should rise and fall once a year, peaking in June, bottoming out in December, keeping perfect time with the Earth's annual speed change. Physicists call this expected pattern annual modulation, and annual modulation is a wonderful thing to look for because it is so hard to fake. Almost anything else that might trigger a sensitive underground detector, any stray background, any contamination, any noise, would not happen to rise and fall exactly once a year with a peak in June, locked to the geometry of the Earth's orbit around the Sunday. That specific yearly rhythm, June high and December low, is a fingerprint that essentially only the dark matter wind could leave, because only the dark matter wind is tied to the Earth's motion through the galaxy. Find that rhythm in your detector, and you may have found dark matter, not by identifying what it is, but by catching it, keeping time with the calendar. Deep under a mountain in Italy, in a laboratory called Gran Sasso, buried beneath roughly 1.5 kilometers of solid rock, there is an experiment that has been looking for exactly this. The rock overhead is there as a shield, blocking out the constant rain of cosmic ray particles that washes over the surface of the Earth, so that the detector underneath can sit in a deep, quiet, particle darkness and wait for something rarer to arrive. The experiment is called Dharma, and over many years of watching, Dharma has reported a signal. It has reported that its detector does register a yearly rhythm, a rise and fall, peaking around June and falling toward December, looking like the annual modulation that the dark matter wind is supposed to produce. That is an extraordinary claim, and I want to hold it the way the science holds it, which is carefully, with both hands, and without rushing. The Dharma result is the single most prominent claim of a positive dark matter detection that exists. And it is also disputed, genuinely and seriously disputed, and it has been for years. The trouble is that other experiments, built to search the same territory, designed to be sensitive to the same kind of dark matter that Dharma's signal would seem to imply, have looked and have not found it. They have not reproduced the modulation, and in science, a result that one experiment sees and others cannot reproduce is a result in limbo. It might be dark matter. It might be some subtle seasonal effect in the detector or its surroundings that also happens to follow the calendar, some background that no one has fully identified. The physics community has not reached agreement. Dharma's signal is real, in the sense that the detector really does show the rhythm. What the rhythm means is unsettled. So, I am not going to tell you that dark matter has been found under an Italian mountain. It has not been settled. What I want you to carry away from Gran Sasso is something better than a verdict, and it is this. Look at the shape of the experiment. Physicists could not catch dark matter by its substance, because it barely interacts with anything, so they did something sideways and brilliant. They decided to catch it by its timing instead. They reasoned that the planet's motion through the galaxy must imprint a yearly rhythm on the dark matter wind, and they buried a detector under a mountain to wait for the year itself to leave a fingerprint. Whether or not Dharma's particular signal turns out to be the real thing, that idea, that you could identify the most elusive substance in the universe by the fact that it keeps time with your calendar, is one of the most beautiful ideas in experimental science. And it is only possible because of the layer of motion we uncovered in the last part. The dark matter wind rises and falls because the Earth speeds up in June and slows down in December. The answer to what is most of the universe made of may, in the end, be hiding inside the seasons. Part 11. The wheel that will roll and the pull of the great attractor. We have been fair to the corkscrew meme. We have admitted that there is real looping in our galactic path, real structure, a genuine flower. We have found the honest origin of the corkscrew shape itself, the 60-degree tilt of the ecliptic against the direction of travel. But there is one last thing the meme gets wrong, and it is worth a moment because it is the final correction, and it dissolves the vortex completely. The meme presents the corkscrew as the shape of our motion, the shape, as if it were a fixed and permanent fact, the true and unchanging form of how the solar system moves. It is not. The corkscrew is a temporary appearance, and to see why, we need one more piece of physics, and it is a piece you already know the name of. It is the conservation of angular momentum. Here is the situation. The solar system's flat sheet, the ecliptic plane, is currently tilted at about 60 degrees to the sun's direction of travel through the galaxy. And you might naturally assume that as the Sun curves around its vast galactic orbit, slowly changing the direction it is heading, the flat sheet of the solar system would turn to follow, keeping the same relationship to the direction of travel, the way a car and everything in it turns together as the car goes around a bend. It does not. The solar system is spinning, the planets orbiting in their sheet, and a spinning thing has angular momentum, and angular momentum is conserved. It does not change unless something pushes on it, and there is nothing pushing on the orientation of the solar system's spin. So the flat sheet of the solar system does not turn to follow the Sun's galactic orbit. It holds its orientation fixed, pointing the same way in space, like a spinning gyroscope holding steady, while the Sun carries it around the long curve of the galactic orbit. And that means the relationship between the sheet and the direction of travel is changing all the time. Right now, the sheet is tilted 60 degrees to the march, and reasonably close to face on, which is why the corkscrew picture is, at this moment, a fair enough thing to draw. But the Sun is curving around the galaxy, and the sheet is holding still, and so the angle between them is slowly turning. After a quarter of a galactic orbit, the orientation will have changed completely. The flat sheet of the solar system will be edge-on to the direction of travel, and when a flat spinning sheet moves edge-on through space, it does not trace a corkscrew at all. It moves like a great wheel, rolling forward along the direction of the Sun's orbit. A wheel rolling through the galaxy. So the corkscrew is not the shape of our motion, it is a phase. It is one pose, held briefly in a slow cycle. The solar system's appearance, as it travels, shifts smoothly from corkscrew to rolling wheel and onward and back, over and over, on the timescale of the galactic orbit. The meme did not just freeze one frame of reference. It froze one frame of a moving geometry. It caught the solar system in a single pose, a pose it happens to be holding right now, and it called that pose the eternal truth. And it is not even that. It is a pose the solar system will set down and pick up again and set down again for as long as the galaxy turns. That is the last correction. The vortex meme is now fully dissolved. There was no privileged frame and there was no permanent shape. There was only a beautiful, layered, ever-shifting motion and a flat animation that captured one slice of it and oversold the slice. And I want to be clear that dissolving the meme is not the same as scolding the people who shared it. The corkscrew animation spread because it pointed at something real. It pointed at the genuine, astonishing fact that our motion through the universe is far richer than the tidy diagram of a few circles, and that instinct was correct. Most people who passed that video along were not trying to deceive anyone. They were responding to a true feeling, the feeling that there is more going on than we are usually told, that the calm sky hides a vast and intricate motion. That feeling is right. The video simply gave it the wrong shape, and dressed the wrong shape in the language of revealed secret truth. And that is the part worth correcting, gently, not because the people were foolish, but because the real answer is so much better than the one they were handed. The real answer does not need to pretend it is forbidden knowledge. It does not need a privileged frame or a single dramatic shape. It is allowed to be exactly what it is, a layered, shifting, honest motion, and it is more beautiful that way than any vortex. But we are not finished, because we have not yet reached the largest layer. We have followed the Earth around the barycenter and the Sun around the galaxy. Now we have to ask how the galaxy itself moves, and here the ground starts to fall away beneath us. The Milky Way is not anchored. It too is in motion, pulled by the gravity of everything around it. Our galaxy and the great spiral galaxy Andromeda, our nearest large neighbour, are being drawn together. They are approaching each other, falling toward a future meeting at a speed of a couple of 100 kilometers per second. And the Milky Way and Andromeda are not alone either. They belong to a small gravitationally bound collection of galaxies, our own little cluster, called the local group, the Milky Way and Andromeda, and a few dozen smaller galaxies, all bound together by gravity. And the entire local group, the whole bound collection, all of it together, is moving. It is being pulled at several hundred kilometers per second towards something. That something has a name that tells you how much we understand about it. It is called the Great Attractor. It is a vast concentration of mass, an overdensity in the way the galaxies of the universe are clustered, and the gravity of it is reaching across an enormous distance and drawing our entire local group toward it. Part of the reason it is still called, simply, the attractor, this somewhat mysterious name, is that it is genuinely hard to study. It lies in a direction that is, from our vantage point inside the Milky Way, blocked. The disk of our own galaxy, all its stars and gas and dust, sits in the way, screening that patch of sky. Astronomers call that screened band the zone of avoidance, the part of the universe our own galaxy hides from us. The Great Attractor is out there, pulling on us, behind the curtain of the Milky Way's own body. There is a strange humility in that. We can measure that our whole local group is being drawn at hundreds of kilometers per second toward a specific direction in the sky. We can feel the pull, in the sense that we can measure its effect, and we cannot get a clear look at the thing doing the pulling, because our own galaxy is standing in the way of the view. It is a little like feeling a steady tug on a rope and not being able to see who is holding the other end, because the rope runs off into a fog. And the picture has only grown larger and stranger as the measurements have improved. The Great Attractor turns out not to be the whole story. There is more mass beyond it, even more distant concentrations of galaxies adding their own pull to the total. The honest current state of the science is that the local group is being drawn across the universe by the summed gravity of enormous structures, some of them so far away and so hard to see that the full accounting is still being worked out. We know we are falling. We are still learning, in detail, toward what. And here, at this scale, the method that has served us all night finally runs out. All night, we have answered the question, how does the Earth move, by choosing a useful frame of reference, the barycenter, the galaxy. Each time, there was a sensible frame to choose, a good chair to sit in. But out here, at the scale of galaxies and clusters and the Great Attractor, there is no convenient local frame left. Everything large is moving, and everything large is being pulled by everything else. There is no nearby still point, no good chair, no obvious thing to measure our motion against. We have run out of local frames of reference. And it would seem that the question, finally, has no answer at this scale, except that it does, because the universe, it turns out, has kept one frame of reference in reserve for us. One last frame, and it was created in the first hour of time. Part 12. The light from the beginning and the stillness in the room. To find the last frame of reference, the one the universe itself provides, we have to go back to the very beginning, to the early universe, long before there were galaxies or stars or planets. In its first hundreds of thousands of years, the universe was a hot, dense, glowing fog. There were no stars yet. There was just an immense ocean of hot hydrogen, simple atoms filling all of space, everywhere, in every direction, glowing with heat, and those hydrogen atoms were in motion. They were moving every which way, this way and that, hot and restless, a vast churning sea of them. They moved in all directions, but, taken all together, the whole ocean of them had an average velocity, a single overall drift, the average of all that restless motion, and that hot glowing fog gave off light. An enormous amount of light. Light pouring out of the hot hydrogen in every direction at once, filling the whole universe. That light was never destroyed. It is still here. It has been travelling for almost the entire history of the universe, stretched and cooled by the expansion of space until it is no longer a visible glow, but a faint whisper of radio wavelength light, and it still fills all of space. arriving at the Earth from every direction in the sky. We call it the cosmic microwave background. It is the oldest light there is. It is the afterglow of the universe's beginning, and it is falling on you, gently, constantly, from everywhere. And here is what makes it the last frame of reference. Imagine you had been there, in the early universe, drifting in that glowing fog, and imagine you were moving at exactly the average velocity of all those hydrogen atoms, drifting along with the overall flow of the ocean. Then the light from that fog would have looked exactly the same in every direction. Look ahead, look behind, look to either side, the same, perfectly even. Because you were moving with the average, nothing was coming at you faster than anything else. But if you were moving at any other velocity, if you had any motion of your own relative to that average flow, then the light would not look even anymore. The light coming at you from the direction you were heading would be shifted, crowded together, made a little more energetic, a little bluer. And the light arriving from behind you, from the direction you were leaving, would be stretched out, made a little less energetic, a little redder. The evenness would break. There would be a faint imbalance, blue ahead and red behind, and the size of that imbalance would tell you exactly how fast and in which direction you were moving relative to the average rest of the early universe. That imbalance is real, and we can measure it. The hot hydrogen atoms are long gone, locked up inside stars now, but the light they emitted still fills the sky, and we can look at it, and we can ask whether it is even, and it is not perfectly even. It is very slightly blue in one direction of the sky and very slightly red in the opposite direction. That pattern is called the dipole, and it is the universe handing us, at last, the frame of reference we ran out of. The cosmic microwave background defines a rest frame for the universe as a whole, the frame of that ancient average flow, and the dipole measures our motion against it. Think about what that light actually is, because familiarity makes it easy to skim past, and it deserves better. The cosmic microwave background is the single oldest thing you will ever encounter. It is older than the Earth, older than the Sun, older than any star you can name, older than the galaxy itself. It set out on its journey before there was a single star anywhere in the universe to shine. It has been travelling across space for very nearly the entire age of the cosmos, the whole long history of everything unfolding while it crossed, and at the end of all that travel it arrives, faint and patient. Here, it is arriving now. It is falling on the roof above you, on the ground outside, on the backs of your hands, a whisper of the universe's first light reaching the end of its journey against your skin. And folded into that ancient whisper, in the tiny imbalance between the light ahead and the light behind, is a message the universe could not have meant to send and sent anyway. The message is your speed. The oldest light there is, simply by being slightly bluer in one direction than the other, is telling you, gently, that you are moving. And when we read that measurement, when we measure the blue ahead and red behind imbalance in the oldest light in existence, we find that the Earth is moving at 368 kilometers per second, give or take about 2, relative to the rest frame of the cosmic microwave background. That is the number. After all the layers, the barycenter and the flower and the bob and the tilted wheel and the pull of the great attractor, the universe itself, through the light of its first hour, gives us one clean final figure for our motion, 368 kilometers per second. We have been pulled to that speed, away from the ancient average, by the gravity of vast overdensities of galaxies, structures hundreds of millions of light years away, the great attractor and the great concentrations of mass beyond it, all of them tugging our local group across the universe. Now stay with me, because here is the strangeness, and it is worth feeling fully. We spent the early part of tonight establishing, with Galileo, that there is no absolute rest, no privileged frame, no true still point in the universe against which all motion can be measured. And that is true. It remains true. The cosmic microwave background frame is not a violation of it. The CMB frame is not absolute rest. It is not the one true frame that Galileo said does not exist. It is simply a natural, universe-wide frame, one particular frame, defined by the average motion of the matter of the early universe, no more sacred than any other, just unusually convenient and unusually grand. And yet, when we measure against it, the universe gives us a real, definite, honest number, 368 kilometers per second. Sit with the pairing of those two facts, because the pairing is the whole heart of the night. There is no absolute rest. Physics is certain of that. And the universe, through the afterglow of its own birth, still answers when you ask how you are moving. It still hands you a number, not the true frame, because there is no true frame, but an honest answer all the same. The universe is not silent when you ask how you move. It does not have a single privileged reply, but it has a reply. So let us assemble the whole thing, all of it, one last time, and see the full choreography. You are sitting in a room. You feel completely still, and in the frame of your own body you are. But the frame of your body is not the only frame, and here is everything else that is true at the same time. You are on the surface of a planet that is turning. That planet is orbiting the barycenter of the solar system, while the Sun orbits that same point in its slow Jupiter and Saturn pirouette, and your orbit itself is breathing, stretching, and turning across the ages. The whole solar system is sweeping around the galaxy at 230 kilometers per second, drawing not a circle and not an ellipse, but a slow, unclosing flower, a rosette of petals you have never once retraced. And as it draws that flower, it is also bobbing, rising, and plunging through the galactic disk every 60 million years, a slow, vertical wave. The flat sheet of the solar system is tilted as it goes, so that from outside it traces, for now, a squished corkscrew, an appearance that will turn, as the ages pass, into a great rolling wheel. And the galaxy that holds all of this is itself falling toward Andromeda, while the whole local group streams at hundreds of kilometers per second toward the great attractor, until, measured against the light of the universe's first hour, the sum of all of it comes to 368 kilometers per second across the cosmos. That is the dance. That is how you are moving through space, actually, honestly, all of it true at once. A turning, orbiting, breathing, sweeping, blooming, bobbing, tilting, rolling, falling, streaming motion, layered 6 and 7 deep, carrying you at hundreds of kilometers per second through a structure so large the mind goes quiet, trying to hold it, and you cannot feel a single bit of it, not one layer. The room around you is perfectly calm. The cup of water on the table is perfectly level. A dropped coin falls perfectly straight. Because you are, and you have been your entire life, exactly where we began tonight. You are in the sealed cabin of Galileo's ship. The portholes are closed. And steady motion, however vast, however layered, however fast, cannot be felt from the inside. The calm of your room is not a lie, and the dance is not a lie. The calm is simply what the dance feels like from within the cabin. This is what the corkscrew meme was reaching for and could not hold. It wanted to tell you that you were moving in some grand and dizzying way, and it was right that you are. Its mistake was to think there was one true picture of that motion, one privileged frame, one real shape, and to freeze a single pose and call it the answer. But there is no one true frame. There never was. And that absence is not a loss. It is the gift. It means you are handed a choice. You can choose the frame of the galaxy and see yourself blooming through the Milky Way at 230 kilometers per second. You can choose the frame of the cosmic background and see yourself streaming across the universe at 368. Or you can choose the frame of the room you are in, the frame of your own quiet body, and see yourself perfectly, completely, restfully still. Every one of those is a true description of you. Not one of them is the illusion. You get to choose the useful frame, the one that fits the moment you are in. And tonight, the useful frame is the room. Tonight, the useful frame is the bed, the chair, the still and level cup of water, and the calm. There is no contradiction in choosing it. You are not pretending, not turning away from the truth, not closing your eyes to the dance. The stillness of the room is every bit as true as the wheeling of the galaxy. It is simply the description that fits the question your body is asking tonight. And the question your body is asking tonight is a small and gentle one. It is asking to rest, so choose it. Let the galaxy turn without you having to feel it. Let the flower draw itself, and the disk go on, weighing its dark matter, and the old light keep arriving from every direction at once, with its faint blue whisper of 368 kilometers per second. All of that is true, and all of that is happening, and none of it asks anything of you. You are moving in 6 nested ways through a wheeling, blooming, unrepeatable dance across space-time. And you are also, right here, in the only frame that your tired body needs tonight, perfectly and completely still. Both are true. The universe permits both. Rest in the one that lets you rest.